Okay, let's begin the next session. The first talk is by Alessandro Romito from Lancaster University, and it's on Unveiling measurement-induced phase transitions trajectory by Cedric.
Thanks. And first of all, let me thank you, the organizer, for having me here. I arrived only yesterday, but from one day impression, the program looks already stunning. My talk today is about measurement-induced phase transitions, and the results I'm going to present are mostly in these two papers. And before I start, let me quickly thank the main actors that made these results possible, my collaborator Graham Kells and Ganit Maiden, but most importantly, my PhD student, Chun Leung, who is currently moved as for a postdoc in Newcastle. And let's start. So measurement-induced phase transition, very broadly speaking, sit into what we can call driven dissipative many-body quantum systems, where many different actors are at play. There's, of course, quantum mechanics, which is coherence and entanglement. There's, in principle, a bath, which disrupt this process, and we also might include some drive or external classical control to the system. Two main aspects will be important for my talk today for this measurement-induced phase transition. One is the fact that the system is many-body, and we are looking at some generic feature of many-body system, mostly in information scrambling thermalization, which all have to do with the fact that the entanglement in the system, due to the quantum interaction between the individual element, grows to an extensive scaling. I will be more precise later with what I mean by volume law. And the other important aspect is that we want to treat the bath, so the openness of the system, the interaction with the external world, as detectors. What is the main difference? That if we think of a bath as detector, we assume that we can keep track of the records of what this detector is measuring about a quantum system, as opposed to a bath in which the information is lost there. So the first step is what is a competition between these two, and we can do that. The seed of all we're discussing today is already there for a very simple, well-known effect in a single qubit system, we would say in modern language. What we can have is a qubit, or if you like, a spin 1/2, and we can assume that this system is evolving according to a unitary dynamics, which you can represent here in this gray square in steps. And this unitary dynamics is punctuated by some projective measurements. So to be very specific, you can have spin 1/2 with an Hamiltonian proportional to sigma x, and you at certain times try to measure sigma z. So what your system would like to do without measurement is to go into coherent oscillation between the North Pole and the South Pole, and if you measure probability to be at the North Pole, assuming you started there, you will see some oscillating dependence. On the other hand, if you start doing measurement at the interval delta t, this is disrupted, and what happens is that you will collapse either back to the North Pole or to the South Pole, and if the measurements are frequent enough, so delta t tends to 0, the probability to be kicked back to the North Pole essentially goes to 1. So essentially, measurement is disrupting these coherent oscillations by localizing your spin to be at the North Pole. Now, this measurement-induced phase transition originates from extending this behavior to many-body system, and the main effect is that now the effect of unitary dynamics is that of scrambling information, which means creating entanglement on a volume low scale across the system. Let's discuss this in the first example, and the first one, which was in which this measurement-induced phase transition were proposed and predicted. So what you can think of is a chain, one-dimensional chain of spin 1/2, and you can have a unitary dynamics, which is given by these gray rectangles. You can think this as a schematics of just a normal Hamiltonian, local Hamiltonian, just this is the evolution in time done in baby steps of interval dt. Or you can equivalently think of this like a quantum circuit which is run on a quantum hardware. So you have this bricklayer structure of these unitary gates, and what they will do will, if you start with a system which is completely disentangled, so imagine some spin up, spin down in some random configuration, what happens if you continue forget about the measurement for now, if you only have the squares for a very long time, is that each spin will become essentially entangled on an extensive scale with all the other spin, and the scale is of the same size of the system. That's what we call volume law entanglement. Formally speaking, the way you quantify that is that you take your system, you cut a partition of it, so you bipartite it into two parts, A and B. You take the state of this system and you trace out the degree of freedom of part of the system, and you're left with the reduced density matrix of the subsystem A. And for this reduced density matrix, you calculate the von Neumann entropy, which is a trace of rho A log rho A. And this quantity is called the entanglement entropy of the system, of subsystem A. Now, what you want to do in this system, and here's where the measurement, the Zeno effect comes into play, you want to punctuate these dynamics by measurement. Now, to make the system as simple as possible, what we can think of is that this gray square don't have any parameter. So we assume that they are completely random 2 qubits unitary gates. So there can be any unitary matrix in the Hilbert space of 2 qubits, chosen at random at each site and at each step in time. And then you can perform measurement, and here is where we introduce the only parameter in this game, which is the probability of performing the measurement at that specific spin. So we measure sigma z at spin with a certain probability p. Now the question is pretty trivial in two cases. If we don't have measurement, as we already said, you will obtain an entanglement which is volume law. So what you expect is that if you take this quantity and you scale it with the system size, there are two ways to do that. Either you keep the total system fixed and you change the size of subsystem A, which is the most natural one. The one that you usually do for numerical reason is that you take the entire system, you cut it the exact half, and then what you scale is the size of the entire system. If you do that, what you want to know, what you expect without measurement is that the entanglement that you reach at steady state will grow linearly with the size of the entire system or of subsystem A. The other limit, which is completely trivial, is the one where you measure with probability 1. You measure everywhere at any time. Then whatever entanglement you created, you for sure will disrupt at each time steps, because each spin will be up, down, and you create at each time a completely unentangled state. So in that case, entanglement is absolutely 0 or 1, depends on how you, in unit of log 2, how you quantify. And that's what happened in the middle. So here you have two examples. This is when you perform with very low probability. So as a function of time, your entanglement grows, and then it saturates to a given state. If the probability measurement is higher, what happens is the entanglement fails to grow and saturates at a much lower level. Now, what you see is a lot of colors here, and the reason is that you have a lot of quantum trajectories because you're doing measurement. These are projective measurements. So what happens is at each time, you can get up, down at each of sites, and this generates a full set of possible readout, and these sets of readout labels all possible quantum evolutions. So each of them will give a different value, and what you see here in this orange line, these are all the possible quantum trajectories calculated under this evolution. What is important to notice is what happened to this steady state value when you change the size of the system. If the probability to perform the measurement is low, you see that the entanglement keeps growing linearly with the system size. What happens instead, if the probability of performing the measurement is higher, is that apart from finite size effect at small value, this saturates to a certain value and fails to grow with the system size. And that's what we refer to area law. That's kind of expected. What was surprising is that the passage between the two is actually a genuine phase transition. What does it mean? It means that system remains on a volume law for certain low value of probabilities. It's area law when the probability is higher, but there is a unique critical point at which the scaling goes logarithmically. So you go from linear to logarithmically to constant. This is a phase transition which is very different from many of the phase transition we had studied in the past. The main reason is that it happens at the level of trajectories, and let me try to explain it in more details soon. Before I do that, that was so surprising that there was a flood of research into the topic, and people started to try to characterize this transition, mostly numerically, with all possible set of ingredients, and you can play with two things. You can play with your quantum coherent dynamics, trying to look at different kind of random or chaotic dynamics, or trying to restrict yourself to specific kind of certain unitary dynamics, or even go to Hamiltonians instead of unitary gates. And also with the measurement, actually, you can play in many ways. You can make projective, continuous measurement. You can post-select to certain trajectory. You can look at quantum jumps versus quantum state diffusions. And what turns out is that all of them essentially have transitions, but the transition depends a lot on what you're doing. So there's a sort of an entire zoo of transition that we are still trying to characterize, I would say. And here you see just an example in which you perform the stroboscopic projective one, which is the gate circuit, which was the original one, in which you have certain probability for your critical value and certain critical exponent. If you change to continuous measurement, which is one of the early work I tried to do in this context, you get completely different critical exponent. And the critical value, of course, differ, but that's not relevant. So message, there's a zoo of transition to be looked at, and we would like to understand more about them. To do that, we need to make a little step from the projective measurement, and here it's all very useful, all what you learned about quantum trajectory and the formalism around it so far, so I can be much faster on this part of the talk. So we want to generalize. We don't only want to do projective measurement, we want to do more general measurement, and actually want to do them in a continuous way. So the way I'm gonna describe the system from now on is through a stochastic quantum evolution. And I will mostly use two kind of approach. One which is based on a Poisson process, which I will refer as quantum jumps. And this is the update of a quantum state depends on a random variable which comes from the detection, which can be 0 and 1, which the probability which is proportional to dt. And this is your Poisson distribution. And what happened is that the evolution of the system depends on the outcome of the measurement, of course, but it also includes some nonlinearity, as you have seen in this term here. So the evolution depends on the expectation value of the state itself. Similarly, you can also obtain continuous quantum state diffusion, which is in this case described by a Wiener process, which is essentially the one in which the readout obey are Gaussian distributed outcomes. Okay, they both share the same thing. The evolution of the state is nonlinear and includes some nonlinearities. How do you go from one to the other? Very simply, the idea, I mean, at least one way to go from one to the other is instead of projecting directly the state, you can think of the detection process as a coupling of your system with an ancillary system on which you perform the readout. What is common to all this is that the readout, of course, depends on the state. Actually, is a stochastic outcome, as a probability distribution that depends on the state, and vice versa, it changes the state in a way that depends on the readout itself. This introduces the nonlinearity in the dynamics. Okay, so why these transitions are special? The transitions are special because they depend on the trajectories, which is not what we are usually used to. So the first observation you want to do is that this kind of equation generates trajectory as much as the projective measurement do. They just usually give continuous trajectory with jumps. Now, you can think this of detector as a bath in the sense that you can trace out and ignore the information the bath is giving to you. So the bath is measuring, but you don't know what the outcome are. In this case, your set of measurements acts like an external bath. You're completely ignorant to the outcome and you lose information. As a result of that, you can only describe the system in terms of your knowledge about it, and the knowledge is encoded in the density matrix of the system, which is averaged over the outcome of the bath because you don't know them. So that's the best description you can have if you don't know what the outcome are. So the best descriptor of the system state will be a density matrix, which is the weighted averages of the evolution of the state along the trajectories, and this is, we know exactly well, we have studied here for tens of years now, how this system evolves. It's a Lindblad equation. We know a lot about it. We know how to calculate things. We know how to calculate the steady states. We know a lot about it. Now, if you follow this path and you ignore the readout of the environment, what you're looking at is the average density matrix, and the best you can do if you want to estimate the entanglement is to calculate the entanglement entropy based on the reduced density matrix. That's a bad idea for many reasons. First of all, if you have a mixed state, the von Neumann entropy is not an estimator of the entanglement. at all, so you get something very wrong. The second reason, which is even more pragmatic, is the fact that if you consider the dynamics that we are typically taking, which you have unitary evolution with non-compatible measurements, the typical outcome of a steady state density matrix that you obtain in average is just a completely flat trivial one. So this is typically proportional to the identity in all the cases that we'll be studying, which is a completely trivial case. So you get nothing out of it. Instead, what you want to do is that you want to follow the system along each individual trajectory. For each individual trajectory, you want to estimate, compute, or measure the entanglement via this entanglement entropy, which now is well defined because, at least for theorists and on paper, the state is a pure state. And then, after you calculate the entanglement entropy for each individual trajectory, you want to average over it. Okay? These are two very different objects. This is trivial, and this is the one that shows the transition. So experiments also usually work under this regime. You average over the measurement readout, and you look at the average state. So one of the questions in this, which is crucial in this context, is whether this quantity is in principle measurable. In principle, yes, but it's also a very, very complicated one. So what I'm showing here is just a sketch of what you would use as a typical experimental setup. You take one of the quantum hardware that exists at IBM or Google or any other quantum info company, and you run a unitary circuit there with local qubits and then perform local measurement, mid-term measurements. So you can generate the trajectory, that's no problem. The problem comes when you have to do the measurement. What you have to do, you have to follow one of these trajectories. So you say you generated one and you have this state after a long time. And now you want to measure the entanglement, which is entanglement entropy, for example, any other entanglement monotone of that state. Crucially, this object is going to be nonlinear in rho, necessarily. So the only way you can extract the measurement from that state is that you have many copies of that state, you measure it repeatedly, and you accumulate statistics about it. So tomography, or you can do some more sophisticated process, but essentially you have to make a tomography of that state. So you need many copies of the state itself, and this means that you need to have many copies, you would like to generate the same dynamics, but now the dynamics is stochastic because you're performing measurements. So if you try to run the same experiment twice, it's not sure you get the same state. And actually, especially in this context, it's very unlikely because you have to perform measurement for extensively in space, roundabout for any qubit you're having, and also extensively in time because you want a steady state. So essentially, the probability that you get the same trajectory scales will be exponentially small in L and T. And you're looking at the phase transition, you would like to go over steady states, you want to go to thermodynamic, both L and T to infinity. So in principle, experimentally, you want to access something which is inaccessible. There have been some attempts to experiments which, at the time they were published a couple of years ago, they were claimed to be the most expensive run of quantum hardware at the time, in terms of hour of running the hardware. And with this experiment, they managed to do decent statistics of up to 8 qubits. That's what the data I'm putting is from an IBM experiment. But anyhow, generically, the idea that this is an exponentially impossible experiment to do goes under the name of post-selection problem in the field. So that's one of the issue with this issue or particularities of this transition, which makes it different from most of the other. The other one is that the transition depends on the trajectory. So we already learned that if we average, we get a different result, but in principle, we could analyze this phase transition for an individual trajectory and ask ourselves whether changing the measurement strength along that trajectory gives or gives not a phase transition, and whether there is a typical trajectory that captured the universality class or the features of the transition, whether this is just a feature that appears in average. And this is the direction I would like to explore here. And the first starting point is to look at one trajectory. And there is a privileged one, as you might imagine, is what I'm going to call post-selected or no-click trajectory. And I'm starting here from the quantum jump version. So as I said before, this is the Poisson variable takes value 0, 1. You can decide to pick a predetermined trajectory, which goes under the name of post-selection. But you decide a priori that you only want to look at trajectory when all the detectors all the time measure 0. If they don't, you throw away the entire experiment, you start again. Okay, that doesn't favor the experiment because once again, you have to throw away an exponentially large number of experiments. So your success probability is still exponentially small, but at this stage, this is a theoretically interesting question because having a theory of this, we don't have a theory for this phase transition, so we need to find a way to simplify that such that we can capture the physics in a way that for which we can have a good theoretical modeling. So if we do that, as you have seen already in other talks, what you're left with is some non-Hermitian Hamiltonian. And this is something we can look at. So the first step that we can do in this kind of business is look at how does this phase transition look like if we do a post-selection, if we look at the post-selected no-click dynamics. Okay, and that's the first attempt that people did on this. So we need a phase transition, we need a many-body system, so we look at simplest thing we know, which is quantum phase transition given in the Ising, one-dimensional Ising in transverse field. So that's our Hamiltonian. And we perform measurement of one local operator, doesn't really matter, but I think in this example was sigma z as well. So what you run everything numerically. And you run numerically two experiments, let me call them. One in which you do the full simulation of all the trajectories, and you extract the transition. Now I'll tell you brief in a second how you do that. And then you repeat the same experiment with the post-selected trajectory, which to be run as a simulation is a very easy experiment because on a computer you can tell them that you get 0 on the update every time. So what do? You run them, and then what you want to do, you want to find the transition. In this case, there's a bit of theory behind that, but the transition is found by fitting the data with this expression. And the reason is that this model is mapped to free fermion, and for free fermion, what we know is that we either have an area law or a log scaling. So we can fit with this log scale, we fit the entanglement entropy with this log scaling, and when the coefficient of log scaling, which would be the central charge of an equivalent conformal field theory, goes to 0, you know that you got a transition. And that's what you plot here. You plot the C extracted from the fit as a function of the measurement strength gamma. And what you see is that when gamma is very large, get 0, which means you're in area law, and then there's a point at which you deviate from them. Now the deviation is different in the two cases. So the green one is the post-selected Hamiltonian, and the green one is the full quantum state diffusion dynamics. But the critical point is the same. So maybe, after all, this transition is captured by all the trajectory, might avoid to do a run of all the trajectory, or might select at least theoretically some specific one and work with them. Yes. So what do, you run the trajectory. Ideally, what you do, you take the trajectory and you calculate the entanglement, and you make an average weighted with the corresponding probability of the trajectory. Yeah. It's not born. It's a probability that comes. This is a continuous dynamic, so it's a probability that you obtain from this stochastic evolution, but it's the same essentially. Yeah, the simulation is a sampling of all the trajectory. That's essentially what you do. You just repeat the simulation many, many times, and that's naturally samples the trajectory according to the Born rule. You need, in principle, exponentially large, yes. That depends on the system size. And the advantage of these, as I said, is that these are free fermion, so these are Gaussian states, which means that you can go to much larger system sizes. That's the reason why this paper focuses on this, and that's also the reason why the rest of my talk will focus on that, which is what I want to discuss here. But yes, in principle, you have to generate tens of thousands of trajectories, but you can still do on a machine, on a classical machine. Okay, so the first question is, how good is that first result that we obtain? Let's take it a bit more generally, and let's look at the case where by now we know something. And I will tell you what we learned about this simple case. I think that this is the case on which we know the most, both numerically and analytically, about this measurement-induced phase transition, which are fermionic Gaussian states. So free fermions, essentially, if you want. So the model I'm considering is continuous dynamics that are just depicted here as a circuit, but essentially what you have is these gray boxes, as before, are the unitary part, or the Hamiltonian, if you want, and the part here are the measurements. So I'm doing a unitary dynamics, and I'm performing 2 measurements which are not compatible at each step. The system is a free one-dimensional chain of fermions. It's just written in terms of Majorana fermions. So if you don't know what they are, just think of a pair of them. The first and the second form a single fermion, and these are just the real and imaginary part of it. But that's not crucial. I mean, it's just needed to be general enough. So the Hamiltonian is just normal hopping. So we have a fermion hopping on the one-dimensional sides. And what you can measure are 2 things. The first one is trivial. The blue one, you measure the local occupation of each site, the local density at one site. The red one is what comes out because you have these Majorana fermions. If you think in terms of a chain, you're measuring some sort of superconducting pairing between nearest neighbor in some way. Okay? But anyhow, it's a quadratic operator in terms of this fermion. So you have 3 parameters here. You have your measurement strength, 2 measurement strength, and actually you can reparameterize in terms of an overall measurement strength and then unbalance between whether you're measuring one or the other operator, and then your Hamiltonian evolution. And that's what happened in terms of phases. So this is a triangular plot. So each side of the plot has one of the parameters put to 0. So if you look at this line here, this would be just a free fermion where you're measuring the density. And what we learned about that after a bit of back and forth between different prediction in the literature, I think we have good agreement now, both analytically and numerically, that there is no transition here. There's only area law. So as soon as you perform measurement, you completely destroy the unitary dynamics. You just localize immediately, no matter how small is the measurement. This came a bit of a surprise, honestly, and took a few papers to different people to come to this conclusion. But if you allow for more generic measurement or more generic dynamics, which is what happened in general here, you do have a transition between an area law and the logarithmic scaling part here. And on the other side, instead, you have a genuine transition between an area law and the logarithmic scaling. Also, this case is just free fermions. The difference is that the unitary dynamics is not charge conserving there after some mapping. So whether there is or there is not a transition for free fermion might depend on extra symmetry constraints that you have on the dynamics. Yes? Which one? Numerical is also, well, numerical you can establish for as much as numerics can tell. So yes, initially the predicted transition, I mean the story, there was a transition, then there was a theory backing up the transition, then there were numerics done with projective measurement telling that probably there is no transition, then there was a theory done with these Majorana fermions here, but with a different unitary predicting that there is no transition, and now we do have a theory that also for the charge conserving cases really predicts. There were a couple of papers predicting no transition actually, and now we do have the full picture for the entire system, which is exactly what I'm depicting here. So whether generically transition is there, but in certain limits, like the one in which you have charge conserving, I'm not sure whether we're not sure whether it's a charge conservation that makes the trick, but for that model of fermions hopping on a chain and measuring the local density, you do not have a transition. Or better, you have a transition immediately as soon as you switch on the measurement. Okay. The other interesting thing is that here you have 2 measurements only, you have no dynamics. These are 2 competing measurements, and they do generate a transition. It's area to area law, but there's a critical point in the middle in which a system scales logarithmically. If you make system more complicated, you can also have measurement only that generates a volume law dynamics if you include in different systems. But anyhow, the point is that if you start analyzing this, you get some strange critical exponent for this one that do not correspond to any phase transition. And if you look at the same system, very good. If you look at the same system from the post-selected trajectory point of view, you do get the same phases. You get 2 different area law phases, and you get a logarithmic scaling one in the middle, but the shape is completely wrong. Here it captures correctly the only area law, but in the other limit, it fails completely to find a transition. So generically, this tells us that in principle, if you look at post-selected trajectory, if individual trajectory, you do not capture generically the feature of the measurement-induced phase transition. So what the final step is whether, I mean, can we go from one to the other? How happens that this single trajectory is missing it? And do we change continuously from this picture to that one? That's one of the first questions we can ask. And also in asking this question, we construct, which is the idea that we do, we want to construct a theory that allows us to calculate the analyze measurement-induced phase transition for subsets of trajectory, which you can arbitrarily tune. This way we can go from one side to the other, but you can also use the tool in general if you want to look at the most probable trajectories and check whether the prediction in that case might be stable or not. So to do that, we do what we call the partial post-selection. So we go back to the microscopic model, in which you have a system coupled to an ancilla that works as a detector, and then this is read out and gives a back action. And I'm using as an ancilla a one-dimensional pointer, so a particle on a line, which is initialized as a Gaussian. The Gaussian interacts with the system via a coupling Hamiltonian with the parameter you want to measure, in this case sigma z of a spin, coupled to momentum. This will induce translations of the Gaussian towards positive or negative, which are proportional to the operator you're measuring, and these end up in a probability distribution for the position for the readout, which is the sum of two Gaussian, which are this brown one, with the relative weight, which is given by the projection of the state onto the eigenvalues of the system you want to measure. What you see is the sum of these two Gaussian, which is a purple object, and you can well approximate this purple object with a Gaussian in the limit in which dt is small, and in the limit in which the shift, the coupling is small in time dt, which means that the two translations are proportional to the square root of time. Okay, so that's our model. And here comes the idea of partial post-selection. Instead of picking a single trajectory, let's just pick a bunch of them and throw away another bunch of them. So we cut this distribution with just a theta function. The green one is the one that you would obtain in general, and we decide to throw away all the experiments if you get a white, if you're in the white region, while you keep the green one. Now, what you do, and here it's part of a theory, you want to approximate this new distribution with the new Gaussian, with the Gaussian one, with the change width and average. And this works, of course, in the limit in which this cut goes to minus infinity, which is the case if you demand that the cut is also proportional to square root dt, and you will obtain an effective description given by this equation here. So this is a modified Schrödinger equation, which includes an extra parameter, zeta here, that we call the degree of post-selection. So essentially, it's a continuous parameter in which if you set xi equals 0, this part survives, while both this part and this part, because the variance of this parameter is exactly this one, this part, which is a stochastic one, disappears, and you're left with a non-remission Hamiltonian. The other thing that you want to do is that the other limit is the one in which xi is equal 1, in which case this non-remission component disappears, and you're left with the standard stochastic Schrödinger equation. Okay? So now we have a theory, we have an equation, a stochastic Schrödinger equation modified with extra parameters, and we use it like a tool to explore the model we discussed. There's a bunch of technical complication here, which have to do with many-body physics, so I will go quickly through them. I'm happy to discuss them in any detail you want later. Essentially, we have to modify this Hamiltonian to include some randomness in the Hamiltonian as well. That no physics needed, this is pure technical purposes to make any calculation analytical. So which means that if you want to compare to the results before, some of the previous results cannot be obtained because we are automatically non-conserving charge here, but the expected we should be able to capture the measurement only in phase transition. The other thing is the quantity you want to calculate. Calculating entanglement entropy is complicated because the nonlinearity comes through a log. So what you want to do, you want to take the simplest entanglement estimator, which is nonlinear in the density matrix. So you want the quantity which is rho square. And you can calculate something which is physical sensible, which is essentially what we call conditional reduced entanglement entropy. And this will be the entanglement entropy between two partitions of the system in which you also include the detector, the ancilla detector that on which you perform the projective measurement. If you calculate that quantity, it's essentially proportional to the unnormalized density matrix square, and you can calculate this quantity assuming that you have two exact copies of the system. Now, at this stage, is in a completely theoretical construction. So you construct a replica of your system and a replica of the exact stochastic dynamics. And in that case, what you're looking is an average of a quantity on a tensor product between the two replica, and the average can now go inside the trace, and you only need the average dynamics of these two replica metrics. So that's a trick. Now we need to calculate an average dynamics of a density matrix, even if these density matrix has some strange correlations in it between the two replica, but it's something which is more doable. And to do that, the last technical trick is that we go to what is called the Choi isomorphism. Instead of evolving density matrix, we just vectorize density matrix. So we put Brian Cat essentially, I mean, this is a very pictorial description where we put Brian Cat in a single vector and we evolve them simultaneously with an Hamiltonian rather than as a joint to the density matrix. This gives us four copies of the chain that have to evolve. I'm done. 1 minute. That have to evolve with an Hamiltonian, and we know how to calculate this and take the average. The analysis is complicated. We bosonize the system, do some RG flow analysis, but we get some analytical result. And that's what they are. So what we show, this is a measurement-only transition, so there's no Hamiltonian here. We know that there's criticality here. What our theory predicts is that the criticality is not changed from the post-selected one if you add trajectories at all. So you should get exactly the same phase transition. The caveat is that our theory only works under an approximation, and that is this parameter xi should be essentially smaller than pi over 8. So it only works as long as bosonization works. So as long as our approximation works, the critical exponent should not change. And this is interesting because that's what we find numerically. So the black dot here are numerical simulations of the full system in which we calculate the critical exponent for different value of partial post-selection. Our theory predicted the exponent should remain 1, which is the one of the Ising scaling until the theory fade, which is the value of psi star where our approximation is broken, and indeed numerically we confirm that. Beyond this point, we cannot predict with the theory what happened, but numerically we see that there is some sudden jump in the critical exponent, which means some sort of phase separation that we don't know how to make a theory of. But this is the main results of our theory, which also gives a sketch of the schematics of how the phase should look like in terms of this partial post-selection. So I described this, and that's my final point. So this will be this is the case. Let me start the other way. This is a fully monitored case in which you have two area law, and then you have a transition to a log square area. If you control the post-selection, the situation looks slightly different. The area law phases are larger when you are partially post-selected. There is an extra new phases due to the post-selection, which is log scaling, and both of them get shrinked as soon as you decrease the degree of post-selection up to a critical point of the order of psi star, in which this sort of transition changes nature. This is the Ising transition. Here the transition becomes something else. And these are the main results, and here are my conclusion. If I can summarize, we did two things. We introduced a new theoretical tool which allows us to calculate the entanglement along a subset of trajectories with this partial post-selected stochastic Schrödinger equation. We applied it to measurement-induced phase transitions, where we discovered that the phase transition is stable for a finite number of post-selection, adding trajectories around a given one, but there is a phase separation at a certain point, which means that a single trajectory cannot give us prediction on the full measurement-induced phase transition. Thanks. Yeah. There's a microphone behind you. No.
Okay. Thank you for the very nice talk. Can you, but I didn't really understand this very important point about this post-selection for the diffusive case. Yes. So exactly, in what sense are you post-selecting, and what would it correspond to operationally?
Okay. So in one, what you can do if you have this, I think this scheme is good enough. This is the outcome from a single step of the process. What you can do, you can choose a single trajectory here, which is the one in which the outcome of your measurement is the one that you obtain. Let's say you're measuring a spin up-down. You want to post-select on the readout of spin up. You can choose one trajectory, which is the one in which you take R, which is the outcome, the most likely outcome that you would obtain if the spin were up. Okay, this corresponds to a given value R in this probability distribution that depends on the state, and you at each stage keep that value. Now, operationally, this is difficult to do because the value you post-select should depend on the state itself. So you should already know what state you're dealing with. But from the theoretical point of view, is a well-defined procedure. So defines a single trajectory post-selection. What I do as a partial post-selection is that I simply cut. I mean, this works because we're measuring an operator with only two possible eigenvalue, which are one positive, one negative. So the distribution we're looking at is a sum of two Gaussians in which one of the outcomes spin down would be negative, one of the other would be positive. So the idea is that if you cut this probability distribution somewhere to the right, you're always favoring more the outcome corresponding to the Gaussian pointing to spin up, corresponding to the Gaussian pointing to spin down. That's the end wavy argument. But in principle, you can perform this calculation and you show that indeed the equation results in this.
Okay, I guess what's surprising to me, what I don't understand, is that you still have the DW, which seems to be the same size regardless of doing the post-selection. But
no, the size of DW is controlled also by this one, because the width of DW is essentially exactly zeta gamma. Okay. I didn't write that, sorry.
Okay, all right, then that makes more sense. All right, thank you.
So exactly. By cutting the Gaussian, you also control the fluctuations of your noise.
Thank you. Yeah, thanks for the talk. So in actual experiments, of course, there is the inefficiency of the detector. And so in the diffusive trajectory like this, you will be faced to density matrices. So do you see any way to work with that?
That's a very complicated question in many ways. First of all, when you have mixed state, already defining the entanglement for mixed state is a nightmare per se. And all the definitions that you have are very difficult are very, let's say, not experimentally friendly, like maximizing on all possible states that give rise to that state. But there are some work, and also, I mean, theoretically we don't have any analytical results for, well, actually we do have one. So the only analytical results we know for this, for inefficient measurement is for free bosons with inefficient measurements. What we know there is that there is a threshold of the measurement after which there is yet another phase transition in which you lose the volume or area law. So you have some sort of inefficient phase transition in this entanglement scaling. And we have some numerical evidence that this transition exists also for spin system, but these are really simulation of 20 spin at most. But in principle, you can work. The message is that there is a tolerance. From these few cases, we have a message which is there is a certain tolerance to a limited amount of inefficiency in which this transition still survives. Of course, we know nothing about whether it's the same transition, whether the critical exponent change, but we can tolerate some inefficiency before losing the physics of this phase transition.
Thanks.